Good afternoon, all. Today we are going to start our next lecture in electronic product design subject. Up to this, in last lecture we had covered the passive components like resistors, capacitor, and now turn next is inductor. In inductor, we have to see role of inductors, all parameters in inductors like hysteresis, eddy current, etc. And also how to study right inductor selection based on which parameters are there. Clear? Now we will start with the first part, introduction part. What is inductor? Okay. For inductors whose magnetic properties rather than electrical properties matter, see electromagnet and inductors are called a coil, choke, or reactors. Is a passive two-terminal electrical component that stores energy in a magnetic field and electric current flow through it. An inductor typically consists of insulated wire wound into a coil. Clear? Inductors, other names are coil, choke, or reactor. It is a passive two-terminal component, electrical component. It has two terminals. Okay. In next section, we will see the inductor, its symbols and all. It stores the magnetic field. Electric current flows through it, and another typical um, what happens when the current flowing through the coil changes, the time-varying magnetic field induces an electromotive force. Okay, in inductor, described by Faraday's law of induction. According to Lenz's law, the induced voltage has a polarity or direction which opposes the change in current that creates it. As the result, inductor opposes any changes in current through them. The inductor is characterized by its inductance, which is the ratio which is the ratio of voltage to the rate of change of current in an international stream of unit SI. The unit of inductance is Henry. Clear? Name for 19th century American scientist Johannes Henry is there. In the measurement of magnetic circuits, it is equivalent to Weber ampere. Inductors have values that typically range from 1 microhenry to 20 Henry. Many inductors have a magnetic core made up of iron or ferrite instead the coil, which serves to increase the magnetic field and thus the inductance. Along with capacitors and resistors, inductors are one of the three passive internal linear circuit elements that makes up electronic circuit. Clear? Inductors are widely used in alternating current electronic equipment, partially in radio equipment. They are used to block AC while allowing DC to pass. Inductors designed to this purpose are called choke. They are also used in electronic filter to separate signals of different frequencies and in combination with the capacitors to make tune circuit used to tune radio and receivers. Clear? Here's the description. An electric current flowing through a conductor generates a magnetic field surrounding it. The magnetic flux linkage generated by a given current I depends on the geometric shape of the circuit. Their ratio defines the inductance L. Thus, L is equals to magnetic flux clear upon current. The inductance of the circuit depends on geometry of the current path as well as the magnetic permeability of nearby material. An inductor is a component consisting of a wire or other conductor shaped to increase the magnetic flux through the circuit, usually in the shape of coil or a helix with two terminals. Winding the wire into a coil increases the number of times the magnetic flux line circuit, increasing the field and thus the inductance. The more turns, the higher the inductance. Clear? More number of turns is there, then inductance is high. The inductance also depends on the shape of the coil, separation of the turns, and many other factors. By adding a magnetic core mode made up of ferromagnetic material like iron instead the coil, the magnetizing field from the coil will induce magnetization in the material, increasing the magnetic flux. The high permeability of a ferromagnetic core can increase the inductance of the coil by factor of several thousands over when it would be without it. Clear? Look at here, this picture. There is inductor, ferrite core and all. An inductor usually is inductor construction is there. An inductor usually consists of a coil of connecting material, typically instead copper wire, wrapped around a core, either of plastic to create an air core inductor or of a ferromagnetic material. Later it is called as iron core inductor. The ferromagnetic material, the later is called iron core inductor. The high permeability of the ferromagnetic core increases the magnetic field and confines it closely to the inductor, thereby increasing the inductance. Low frequency inductors are constructed like transformers with core of electrical steel laminated to prevent eddy current. Soft ferrite are widely used for core above audio frequencies since they do not cause the large energy losses at high frequency that ordinary iron alloy do. Inductors come in many shapes. Some inductors have an adjustable core which enable changing of the inductance. Inductors used to block very high frequencies are sometimes made up of stringing a ferrite bed on a wire. Small inductors can be etched directly onto the printed circuit board by laying out the stress in a spiral pattern. Some such planar inductors use a planar core. Small value of inductors can also be built on integrated circuit using same process that are used to stress make interconnects. Aluminum interconnect is typically used. Laid out in a spiral coil pattern. However, the small dimensions limit the inductance and it's far more common to use a circuit called gyrator that uses a capacitor and active components to behave similarly to an inductor. Regardless of the design, because of the low inductance, the low power dissipation on die-inductor allow. They are currently only commercially used in high-frequency RF circuits. Shield, shielded inductors. Inductors used in power regulation systems, lighting, and other systems that require low noise operating conditions are often partially or fully shielded. In telecommunication circuits employing induction induction coils and repeating transformers, shielding of inductors is closely proximity reduces circuit crosstalk. Clear? There are different types of inductors. First is air core inductor. The term air core coil describes an inductor that does not use a magnetic core made of a ferromagnetic material. The term refers to the coil wound on plastic, ceramic, or other non-magnetic form, as well as those have only air inside the windings. Air core coils have lower inductance than ferromagnetic core coils, but are often used at high frequencies because they are free from energy losses called core losses that occurs in ferromagnetic core, which increases the frequency, a side effect that occurred in air core coils in which the winding is not rigidly supported on a foam is microphony. Mechanical vibration of the windings can cause variation in the inductance. Next is radio frequency inductor. At high frequencies, particularly radio frequency inductors have higher resistance and other losses. In addition to causing power loss in resonant circuit, it can reduce the Q factor of circuit, broad, broadening the bandwidth in RF inductors, which are mostly air core type. Specialized construction techniques are used to minimize these losses. The losses are due to these effects. Which effects are there? First is skin effect. The resistance of a wire to high frequency current is higher than its resistance to direct current because of skin effect. Radio frequency alternating current does not penetrate far into the body of conductor but travels along its surface. For example, at 6 MHz, the skin depth of copper wire is about 0.001 inches, that is 25 micrometers. Most of the current is within this depth is of the surface. Therefore, in a solid wire, the interior portion of the wire may carry little current, effectively increasing its resistance. Next is proximity effect. Another similar effect that also increases the resistance of the wire at high frequency is proximity effect, which occurs in parallel wires that lie close to each other. The individual magnetic field of adjacent turn induce eddy current in the wire of the coil, which cause the current in the conductor to be concreted in a thin strip on the side near the adjacent wire. Like skin effect, this reduces the effect cross-sectional area of the wire conducting current, increasing its resistance. Clear? Where proximity effects happen, parallel wires that lie on each other. That time, adjacent turns induce the eddy current. Clear? Next is dielectric losses. The high frequency electric field near the conductor in a tank coil can cause the motion of polar molecules in nearby insulating materials, dissipating energy as heat. So coils used for tune circuit are often not bound on a coil form, but are suspended in air, supported by a narrow plastic or ceramic strip. Is there clear? Next is parasitic capacitance. The capacitance between individual wire turn of a coil, called parasitic capacitance, does not cause does not cause energy losses but can change the behavior of the coil. Each turn of the coil is at a slightly different potential. So this electric field between neighboring turns stores charges on the wire. So the coil acts as it is has a capacitor in parallel with it. At a high enough frequency, this capacitance can resonate with the inductance, so the coil forms a tuned circuit, causing the coil to become self-resonant. To reduce parasitic capacitance and proximity effect, high QRF coils are constructed to avoid having many turns laying close together, parallel to one another. Clear. Next step is ferromagnetic core inductor. Here is the variety type of ferrite core inductors and transmitter diagrams. Seen corner. Ferrite core inductor type. Ferrite core in iron core inductors use a magnetic core made up of ferromagnetic and ferrimagnetic materials such as iron or ferrite. These material increases the inductance. The magnetic core can increase the inductance of the coil by a factor of several thousand by increasing the magnetic field due to its higher magnetic permeability. However, the magnetic properties of the core material cause several side effects which affect the behavior of the inductor and require special construction. First is core losses, a time-varying current in the ferromagnetic inductor which cause a time-varying magnetic field in its core. Clear? Cause energy losses in the core material that are dissipated as a heat due to two processes. One is eddy current, second is hysteresis. Eddy current. From Faraday's law of induction, the changing magnetic field can induce circulating loops of electric current in conductive metal core. The energy is in this current is dissipated as heat in the resistors of the core material. The amount of energy loss increases with the area inside the loop of current. Next is hysteresis, changing or reversing the magnetic field in the core also cause loss due to the motion of the tiny magnetic domains. It is composed of the energy loss is proportional to the area of hysteresis loop in the BH graph of the core material. Material with low coercivity have narrow hysteresis loop and so low hysteresis losses. Core loss is nonlinear with respect to both frequency of magnetic fluctuation and magnetic flux density. Frequency of magnetic fluctuation in the frequency of AC current in the electric circuit. Magnetic flux density corresponds to current in the electric circuit. Magnetic fluctuation gives rise to hysteresis and magnetic flux density causes eddy current frequencies. and over limited frequency spans, core losses may be treated as a linear function of frequency with minimal error. However, even in the audio range, nonlinear effects of magnetic core inductors are noticeable and concern. Saturation. In the current, if the current through the magnetic core coil is high enough, that is, the core saturates, the inductance will fall and current will rise dramatically. This is nonlinear threshold. This is nonlinear threshold phenomenon and result in distortion of the signal. For example, audio signal can suffer intermodulation distortion in saturated inductors. To prevent this, in linear circuit, the current through ion core inductors must be limited below the saturation level. Some laminated core have a narrow gap in them for this purpose, and powered icon core have a distributed in gap. These allow higher level of magnetic flux, thus higher currents through the inductor before it sat- saturates. Pure point dimensionation. Jaishi. If the temperature of ferromagnetic or ferrimagnetic core rise to the specific level, the magnetic domain dissociate and the material becomes paramagnetic, no longer able to support magnetic flux, the inductance falls and current rise dramatically. Similarly to what happened during saturation, the effect is reversible when the temperature falls below the pure point. Magnetic flux resulting from current in the electric circuit will realign the magnetic domains of the core and its magnetic flux will be restored. Curie point of the ferromagnetic material is quite high. Iron is highest at 770 degrees Celsius. However, for some ferromagnetic material, the Curie points can be close to uh, ambient temperature. Next is laminated core inductor. Here is the picture of it in this right side. Look at this picture. Laminated core inductor. Low frequency inductors are often made with laminated core to prevent eddy current. Okay, laminated core inductor is made up of to prevent the eddy current. Clear? Using construction cylinder to transformer. The current is made up of stack of thin steel shield or laminations oriented parallel to the field with an insulating coating of the surface. The installation prevents eddy current between the shield so any remaining current must be within the cross-sectional area of the individual lamination, reducing the area of the loop and thus reducing the energy losses greatly. The lamination are made up of low conductivity silicon steel to further reduces eddy current losses. Next is ferrite core inductor. For high frequencies, inductors are made up with core of ferrite. Ferrite is a ceramic ferromagnetic material that is non-conductive, so eddy current cannot flow within it. The formulation of ferrite is XSFe2O4, where Xs represent various metals. For inductor core, soft ferrite are used which have low conductivity and thus low hysteresis losses is there. In power iron core inductor, another material power iron cemented with a blender. Here is the hysteresis loss and eddy current loss. What is the difference there? Okay. In all electronic motors experience rational losses during the conversion of electric power to mechanical power. These losses are generally categorized as magnetic losses, mechanical losses, copper losses, brush losses, or stray losses, depending on underlying causes and mechanism. Included in the category of magnetic losses are two types: hysteresis loss and eddy current loss. In hysteresis loss is caused by the magnetization and demagnetization of the core as current flow in the forward and reverse direction. As the magnetizing force, that is current, increases, the magnetic flux increases. But when the magnetizing force, that is current, is decreases, the magnetic flux does not decrease. It de- doesn't decrease at the same rate, but less gradually. Therefore, when the magnetizing force reaches zero, the magnetizing force must be applied in negative direction only. Okay. Relation between the magnetizing force H and the flux density B is shown on the hysteresis curve or loop. The area of hysteresis loop shows the energy required to complete a full cycle of magnetizing and demagnetizing, and the area of the loop represents the energy lost during the process. Look at this graph. BH graph. B means plug. V means flux density. H means magnetizing force. A hysteresis loop shows the relation between the induced magnetic flux density, that is B, and the magnetizing force H. It is often referred to as a BH loop. Clear? The equation of hysteresis loss is given as Pb. Hysteresis loss is generated by Pb. P suffix B. Pb stands for hysteresis loss. W. It is a statement hysteresis coefficient depending on the material used. Which material is used? Bmax is the maximum flux density. Next is eddy current loss. Eddy current losses are the result of Faraday's law, which states that any changes in the environment of the coil of wire will cause a voltage to be induced in the coil, regardless of how the magnetic change is produced. Thus, when a motor core is rotated in a magnetic field, the voltage or EMF is induced in the coil. This induces EMF causing circulating current to flow, referred to as a ED current. The power loss caused by these currents is known as ED current loss. Motors, armature core use many thin pieces of iron rather than a single piece because the resistance of individual piece is higher than the resistance of one solid piece. This higher resistance due to the smaller area per piece reduces eddy current and is tuned eddy current losses. The limitations are installed from each other with in aqua coating to prevent the eddy current. See this second and third job. Current from jumping from one laminations to another. Here is the equation. PE is equals to KE into B max square into F square plus T square into V. Here PE is eddy current loss, KE is eddy current constant, V is flux density, F is frequency of magnetic reversal per second, P is material thickness, and V is volume. Now next is variable part. Sorry, variable inductor. I switch this. Suddenly I move towards the hysteresis loss and eddy current loss because there is while explaining there is a two words are there hysteresis and eddy loss but you don't know. That's why I first explained that one and now moving towards the variable inductor also. Probably the most common type of variable inductor today is one of is movable ferrite magnetic core, which can be solid or screw in our out of the coil. Moving the core further into the coil increases the permeability, increasing the magnetic field and the inductors. Many inductors used in radio application use adjustable cores in order to tune such inductors to their desired value. Since manufacturing processes have certain tolerance, sometimes such cores for frequency above 100 MHz are made from highly conductive non-magnetic material. Clear? Now applications. Okay. Inductors are used in extensively in analog circuits, signal processing circuit, okay, in electrical transmission is their application area. Now, last part is inductor parameters and specifications. When selecting a inductor, it is necessary to understand the parameters and specifications found in the datasheet. Clear? Like any electronic component, there are several parameters and specifications that are associated with inductors. The inductor parameter and specification enable the component to be satisfactorily described and correctly used within the circuit. The various parameters that can be used enable the inductor performance to be fully specified so that it can confidently used within the required circuit. This is the symbol for inductance. Key parameter for any inductor is its inductance. The inductance is the property of an inductor that tends to opposes any change in current flowing. The SI unit of inductance is the Henry. Okay, inductance of a circuit is 1 Henry if the rate of change of current in a circuit is 1 ampere per second, and this results in electromotive force of 1 volt. The actual level of the inductance is influenced by many factors, including the number of turns in the coil diameter, and in particular the core used within the coil. Okay. Second parameter is DC resistance. Another important another important inductor parameter is a DC resistance. It exhibits as inductors are often manufactured from very thin wire. The DC resistance can sometimes be significant even when thicker wire is used. It is still an important factor because it can significantly affect the overall performance as an inductor. The DC resistance can be considered to be in series with the pure inductor for the sake of most circuits simultaneous, although it is a dis- distributed throughout the inductor. The DC resistance measures with a steady current is normally specified in ohm and typically given as a maximum value as it is sometimes difficult to control accurately. Next is saturation current. Next factor is considered, that is saturation. The saturation current is another parameter or specification which is of importance for the inductor. In an inductor, it is possible to saturate the core because there is a limit to the level of magnetic flux. A magnetic core such as iron, ferrite, or another compound can take when it occurs the relative permeability fall, and in turn this causes the level of inductance fall. The saturation current is generally taken to be the current at which the level of inductance falls by a specified amount. Figures of the 10% are often used for inductor with ferrite loss and 20% for those with iron powered core. Next is incremental current. Often inductors run with a bias current passing through them. For example, it may be constant current for a transistor collector where the inductor is in a collector circuit itself. There is a drop in inductance which is caused by this current, and it is necessary to understand this so that the current will be able to operate satisfactorily even when the DC current bias current is flowing. The incremental current inductor parameter is generally takes as the DC bias current flowing through the inductor can cause the inductance to fall by 5% from the initial value with 0. Next is rated current. Another important inductor parameter is rated current. This specification is the maximum continuous current that the inductor can withstand. Generally, the limiting factor for this parameter is the temperature rise of the inductor. with thin wire being used in many inductors to keep the size to a minimum. The current flow can result in power being dissipated in the inductor with the result that the temperature rises. Undue temperature rise can reduce the reliability of even cause catastrophic picture failure of some circumstances. Next is core permeability. The permeability of an inductor core is a key parameter. It governs the inductance of an inductor for a given inductor geometry. Higher permeability core material result in inductor providing the higher level of inductance. The core material as well as the core shape, size, and geometry affect the overall effective permeability, and therefore these factors also need to be taken into consideration as well. Second is next is winding self-capacitance. Inductor self-capacitance or distributed capacitance is a particularly important parameter in many applications. It arises from the fact that apart from adding inductance, the wire also have a small but appreciable level of capacitance between each other. The diagram shows the inductive capacitor within the inductor as seen a simplified way of showing the self-capacitance. However, the capacitance is distributed throughout the whole inductor and it is not separate capacitance. Next parameter is self-resonant frequency. In view of the self-capacitance or distributed capacitance, the inductor form a parallel resonant circuit as shown. All the points where the inductor resonant, the inductive reactance and the capacitive reactance will be cancel each other out and the overall impedance of the circuit will fall to a value governed by the DC resistance of the circuit. Below the resonant frequency, the inductive reactance will be dominate, whereas above the self-resonant frequency, the capacitive reactance will dominate. As a result, inductors are normally used below their self-resonant frequency to ensure that the effect of the self-resonance are not experienced. These are the different parameters which we have to consider while selecting proper inductor. In this lecture, we study inductor, their types, their functions, material used for making inductors, parameters and specifications. Thank you for today's lecture.